Hi, welcome to our CompTIA Network Plus course. In this lesson, we're going to talk about networking topologies, architecture, and types, and we'll discuss the following, such as the mesh topology, the star and hub topology, hub and spoke topology, spine and leaf, point-to-point, three-tier hierarchical model, collapse core, and the traffic flows. So, understanding network topologies, architecture, and types is fundamental to designing and managing efficient, reliable, and scalable network systems. These concepts provide a framework for organizing and managing network connections, ensuring seamless data flow and communication within the network environment. Network topology refers to the physical or logical arrangement of interconnected devices within a network, defining the communication paths between them. Common topologies include the bus, star, mesh, and ring, and each with its unique characteristics and advantages. Network architecture, on the other hand, describes the overall structure and organization of the network, encompassing the design principles, protocols, and technologies used to manage data flow and communication between various components. Network types further defines specific technologies and protocols to build and operate the network. Examples include LAN, WAN, MAN, VPNs, each tailored to a specific need, right? And environment. So a thorough understanding of these concepts enables network professionals to select appropriate topologies, architectures, and network types that best suit the specific requirements of their network. So the first topic is mesh topology. So a mesh topology is a network configuration where every device is directly connected to every other device in the network. So this creates a highly interconnected system with multiple paths for data transmission. In a mesh topology, each device has a dedicated connection to all the other devices, forming a complex web of connections. This approach offers several advantages, making it suitable for applications that prioritize redundancy and fault tolerance. So one of the key benefits of mesh topology is its high redundancy. So if one connection fails, data can still flow through alternative paths, ensuring uninterrupted communication. This is important for critical infrastructure and mission-critical applications where network downtime can have significant consequences. Another advantage is its inherent fault tolerance. If a device fails, the remaining devices can still communicate with each other, reducing the impact of the failure. So the multiple paths also allow for load balancing, distributing traffic evenly across the network and improving the performance. Another type of topology is the star or the hub and spoke topology. So the star hub spoke topology is a commonly used network configuration characterized by a central hub, which is this one, or switch that is connected to all other network devices, forming a star structure. This central node acts as a central point for data transmission and management, simplifying network administration and providing a centralized point of control. So in this topology, all communications between devices must pass through the central hub or switch. And this architecture offers several advantages, making it suitable for various network environments. One significant advantage is its centralized management. With a single point of control, network administrators can easily monitor and manage the network, making troubleshooting and configuration changes more straightforward. So the star topology, simplicity, and ease of management are also key benefits. The configuration is relatively straightforward, making it ideal choice for small to medium-sized networks, such as office networks and home networks. However, the star hub spoke topology has some limitations, particularly in terms of scalability and fault tolerance, right? If the central hub, this one, or the switch fails, the entire networks become disconnected, disrupting communication between all devices. Another drawback is the potential for performance bottlenecks, especially in high traffic networks, as all traffic must pass through the central hub, right? it can become a single point of failure, so potentially leading to congestion and reduced performance. So despite these limitations, the star and hub and spoke topology remains a widely used and practical network configuration, particularly for smaller networks where simplicity and centralized management are being prioritized. Let's talk about the spine and leaf architecture. So the spine and leaf architecture is a modern data center design that prioritizes high bandwidth, low latency, and scalability. It is designed to handle the ever-increasing demands of today's data centers, where high-performance computing and massive data storage are important. The spine and leaf architecture is a hierarchical model where the network is structured in two layers, which is the spine, let's say this one, and this is the leaf. Okay, so the spine layer here on top acts as the core of the network, providing high-speed connectivity between the leaf layer and other network segments. The leaf layer here connects to servers, storage devices, and other devices. And this architecture ensures efficient data flow and reduces congestion by distributing traffic across multiple paths. So one of the key advantages of the spine and leaf architecture is its scalability. It allows for the addition of new servers and other devices without impacting existing network performance. So this means you can add more switches here. Not a problem, right? So in some environment, in some vendors, they can have like an intermediary leaf in between just to scale up, interconnect the devices. So some platforms does support this setup. Let's talk about point-to-point topology. So this is the simplest one, right? So a point-to-point topology establishes a direct, dedicated connection between two network devices, forming a simple and efficient communication pathway. This dedicated link ensures uninterrupted communication between the two connected nodes, offering high bandwidth and minimal latency for data transmission. This topology is ideal for applications demanding high-speed data transfer, such as connecting servers, routers, or switches to create a high-performance network backbone. The absence of intermediate devices eliminates potential bottlenecks and latency, ensuring rapid and reliable data flow. This simplicity also simplifies network management and troubleshooting as the connection is isolated between the two endpoints. Okay? All right, now let's talk about the three-tier hierarchical model, and this is a very important concept when you're starting to learn networking. So the three-tier model is a widely used network design approach that structures the network into three distinct layers: the core, the distribution layer, and the access layer. This layered approach provides a systematic way to organize and manage network traffic, ensuring efficient data flow and scalability for various network environments. Each layer serves a specific purpose and handles different types of network traffic, so creating a well-defined hierarchy that enhances performance, security, and manageability. This hierarchical model enables network administrators to manage and troubleshoot network issues more effectively. Let's talk about each of the layer quickly. First one is the core. So the core layer, which is in here, is the heart of the hierarchical network, serving as the high-speed backbone that connects various network segments, including data centers, branch offices, and remote users. It's responsible for transmitting large volumes of data quickly and reliably across the network. And the core handles the critical traffic flows, ensuring smooth and efficient communication within the network. So if you could compare these to our streets or roads, right, this is your main highway, the core. So when you want to go from, let's say, from one US state to another US state, right? So you gotta have to go to a specific big and long highway. That could be the core layer. The smaller streets, that could be the distribution and the access layer. Let's talk about the distribution layer, which is here. So the distribution layer acts as the intermediary between the access layer and the core layer. It's responsible for aggregating traffic from multiple access layer devices, applying network policies, okay, and routing traffic to its destination. So imagine the distribution layer as a traffic control center for the network. It receives data packets from various access points, analyzes the information, and determines the best path for the data to reach its final destination. This layer plays a vital role in ensuring efficient data flow, balancing network load, and enhancing network security. So additionally, the distribution layer is typically implemented using switches or maybe routers with advanced features like ACLs, access list. You can have quality of service, QoS, and other network management function. It enables network administrators to enforce policies, segment network traffic, and prioritize certain types of data, ensuring that critical applications receive the necessary bandwidth and security. And the third layer is the access layer. The access layer is the entry point for devices into the network, acting as the bridge between the user equipment and the wider network infrastructure. It provides the necessary connections for end devices such as computers, printers, servers, and mobile devices to access the network resources. So this layer is like typically implemented using switches or access points, which provide a physical connection and manage network traffic at the device level. So the access layer, as I've said, is the first point of contact for security requirements. So here you can implement port security, of course, VLANs, and other access control mechanisms to restrict unauthorized access and protect the network from potential threats. This layer also plays a crucial role in the network performance, managing traffic flow, and providing quality of service to ensure the critical applications receive the necessary bandwidth and prioritization. So what is the collapse core? Right? So the collapse core architecture represents a streamlined network design approach that combines the functionalities of the core and the distribution layers into a single layer. This consolidation offers several advantages, particularly for smaller network environments where the complexity of a traditional three-tier model might be unnecessary. By merging the core into distribution layers, the collapse core architecture simplifies the network design and management. And this approach eliminates the need for separate devices and configuration, reducing the overall complexity of the network. All right, so as you will see here, that's the reason why this is called collapse core, because we mixed the core and the distribution layer into one layer, but of course you will still have the access layer at the bottom. So traffic flows. So understanding traffic flow patterns is important for effective network design. So to manage traffic flows refer to the way data moves within the network, and comprehending these patterns is important for optimizing network performance, the security, and the overall efficiency. So by analyzing the types of traffic and how it moves throughout the network administrators make informed decisions regarding network infrastructure capacity planning and security measures. So different network environments have unique traffic flow patterns. For example, the data centers typically experience high volumes of data exchange between servers, storage devices, and applications. In contrast, office networks might see some more user-generated traffic, such as web browsing, email, file sharing. So analyzing these traffic patterns helps identify areas for improvement, such as bandwidth, bottlenecks, security vulnerabilities, and inefficient routing configuration. So the first traffic flow is called NS traffic, or what we call as the north-south traffic. So the north-south traffic refers to the data flow between the internal network, let's say this one, and the external network, like that. This type of traffic is essential for communication with outside world, allowing businesses to access the internet, connect to remote servers, and share data with partners. It also allows employees to access cloud-based applications, connect to remote desktops, and collaborate with colleagues outside the organization. So, north-south traffic plays a very important role in network security. It requires careful management to prevent unauthorized access, gotta protect sensitive data, and mitigate security threats. Network administrators must implement appropriate security measures to control inbound and outbound traffic, ensuring only authorized communication is allowed. And this often involves using firewalls, intrusion detection systems, and other security technologies to monitor traffic, block malicious activity, and prevent data breaches. And the other type of traffic is the east-west traffic. So the east-west traffic refers to the data flow that occurs, this one, right? That occurs within the internal network. So connecting different devices and systems within the same organization. This type of traffic is important for efficient communication and collaboration within the organization. Think of it as an internal communication of network, enabling users to share files, access applications, and collaborate on projects seamlessly. All right, that's the end of the lesson. Here we spoke about the mesh topology, the star and hub and spoke topology, spine and leaf, point-to-point, the three-tier hierarchical model, collapse core, and the traffic flows. Thank you very much for watching the video.